Ano କରୁଛୁ তুই?
Good afternoon, Dr. Abhijit Kundu. Am I audible? It's Aniruddha Sarkar from Greater
Yes,
Kolkata College.
yes, you are audible.
Okay, sir. So I
Uh,
guess many people have joined already. So we will start after 5 to 10 minutes. Okay.
okay.
So everybody is requested to just mute your audio, and
Okay, no problem.
Professor Abhijit Kundu will deliver his lecture shortly. So please, every participant, please mute your audio. All the participants, please wait for 5 minutes. We will start today in our today's lesson within 5 minutes. Okay, we will start our session within 5 minutes.
Hello, Aniruddha sir, are you listening?
Yes, sir, I'm audible.
Yes, yes. Please start the session.
Okay, thank you, sir. With your due permission, now I am starting the session. So, good afternoon, participants. It's Aniruddha Sarkar from Greater Kolkata College of Engineering and Management. So, in today's session, Professor Dr. Abhijit Kundu will present a lecture from his domain of expertise. Professor Dr. Abhijit Kundu is from Chaibasa Engineering College, Government of Jharkhand. So he has received his. I would like to previously first of all I would like to before hand over the entire charge to Professor Dr. Abhijit Kundu, I would like to give a short introduction about him. So he has received his BTech and MTech degree with specialization in electronics and communication from West Bengal University of Technology in the year 2007 and 2010 respectively. He has also completed his PhD from the same university from West Bengal University of Technology in 2019. So his research domain was nanostructure, high frequency device, and photodetectors. He has obtained his research associate degree from biomedical engineering from IIT Gandhinagar in the year 2019 and 20. At present, he is working as an associate professor in Chaibasa Engineering College under Government of Jharkhand, India. His research interest is focused on terahertz electronics, semiconductor device based on wide band gap semiconductor, photosensor, nanobiosensor, and medical electronics and instrumentation. He has published more than 33 peer-reviewed research papers on terahertz electronics, semiconductor devices, and biomedical photosensors. Dr. Kundu is also a life member of IET and CSI, and he has completed AICT-sponsored project as a principal investigator also. He's an empaneled examiner, moderator, and PhD supervisor under public and private universities. He has guided more than 35 postgraduate theses and 3 PhD theses as supervisor and joint supervisor. Now, with this short, brief introduction regarding Professor Dr. Abhijit Kundu, now I would like to hand over the entire charge to Dr. Kundu. Sir, please continue. The entire platform is yours.
Okay. Just wait 1 minute. I will start.
Okay, yes.
My voice is clear.
Yes, your voice is absolutely.
This is a full screen, na? Hello. This screen is visible. Slide.
Yes, yes, visible, but not
Yes,
in full screen.
Full
yes,
screen,
sir,
na?
it is visible, but not in full screen, right?
Okay, it is not full screen.
Yeah.
Again, I want to try. Now it is full screen.
No, still no.
No, sir.
Okay. Just wait 1 minute. Okay. So today we want to discuss about the topic that is the. So first of all, good afternoon to all of you. Now I want to start the discussion of the topic, the improvement of the photodetector performance for photon energy detection in UV, visible, as well as IR wavelength region. So we know that what is a photo detector. Now, actually, the researcher and industrial persons are trying to implement the photo detector because there is a huge application of the photo detector. It can be used medical imaging purpose, defense, as well as the industrial section. So and as well as communication section. So lot of the researcher and industrial persons are trying to improve the performance of the photo detector. Just wait 1 minute. I want to change my slide, but there is some problem. Yes, now the slide check. Uh, the introduction section, I want to some part of this part regarding this part is most of uh, the development of the photo detector. Just wait 1 minute. Yes, the development of the photo detector is in its third generation. The market demand of the photo detector is increasing day by day. Security, defense, industries, and smart healthcare system. The researcher and industrial professionals are working together to meet the market. Recently, the pattern has been developed using the low bandgap or bulky semiconductor material. Sometimes the protector has been reported by the several researchers and the scientists. Most of the protector has been developed using the wide band semiconductor like silicon carbide, gallium nitride, gallium arsenide. This called the there is some limitation of there using the wide band semiconductor. Most of the cases we have been observed that the conductivity is not up to the mark. So the researchers are trying to replace that wide band gap material using the 2D material like graphene, um, uh, hexagonal boron. So here I also want to discuss the properties of the wide band gap semiconductor, elementary semiconductor, as well as the 2D band gap semiconductor. So what are the properties? So this slide is visible to you?
Hello, sir. No, your slide is not changing. The
Okay,
first
okay.
slide is visible.
Just wait 1 minute. Again, I want to share and then
Sir, have you the same file in PDF format? Then I think it can be changed.
okay. Now this slide is visible.
Yes, visible, but not changing your slide.
देखो तो this is the optical spectrum. It is slide visible.
No.
No, sir.
No,
Your
sir. No,
slide.
sir.
Slide is still here.
It is
Okay, okay.
the entire slide has been stick to the first page.
Right.
Okay, okay, okay. Just 1 minute. I want to again try to stop sharing. It is happened.
Sir, just
Just wait
you
one
can
minute.
convert it. Yes, convert it into PDF. Then you can.
Oh, okay, okay. First need to convert the PDF then sharing. Na?
Yes.
Yes.
So it will take some time. I just request all of you, please give me just that time.
Yes, sure.
Okay, sir. Okay, sir. Take your time, sir.
Participants are requested to wait for a while. Sir will start.
Now the
Just
slide is
one.
changing, right? Started changing. I don't know. Maybe there is some problems.
Just wait 1 minute. Few minutes. I just. Just wait a few minutes. Yes, done. I want to share. Now need to full. And now it is visible. Hello,
Yes, sir, absolutely.
Hello, sir. Now it's visible.
it is visible.
Yes, it's
Right,
visible.
sir, it is absolutely
Yes,
visible.
देखो तो एक बार
yes,
slide
yes. It is. It is changing, sir. The slides are changing.
Okay. Moment.
Now it is also good, sir.
Okay. So now I want to start from the beginning again. Today we want to discuss the improvement of the photo detector performance for photon energy detection in UV as well as visible as well as IR wavelength region. So actually, we know that the concept of the photo detector, but here we want to discuss how the performance of the photo detector increment is possible. That part I also want to discuss here. Because the photo detector is very important. There is a various application of the photo detector in medical, defense, as well as defense industries. So, and the performance of the photo detector is not up to the mark. There is a huge scope for the betterment of the performance of the photo detector. Okay. Introduction section I have already discussed that to discuss. Nowadays, the development of the photo detector is in third generation. The market demand of the photo detector is increasing day by day for application in research, security, defense industries, and smart healthcare system. The researcher and industrial professionals are working together to meet the market demand. Recently, the photo detector has been developed using the wide band semiconductor as well as lower band gap semiconductor, and that presently the 2D material is also at the attention of the researcher for the development of the photo detector due to its electrical and optical properties. So now I want to move what is the electrical and optical property of the elementary semiconductor, wide bandgap semiconductor. So this slide is the silicon gallium arsenide compound semiconductor as well as elementary semiconductor is there. So gallium arsenide, gallium nitride, silicon carbide, we can use for the development of the photo detector, as well as we can use the silicon material, but there is some limitation. So for that, the performance of based on this material is not up to the mark. So we can move for the 2D material where the electrical and optical property is better than this compound as well as the elementary semiconductor. Now, this is the property of the 2D material properties. Mainly we use the graphene and boron nitride. Graphene, we have to remember the graphene is a 2D material, but where the band gap is very low. So if you use the only the graphene material, so it is not possible to improve the performance because the band gap energy is low. So anyhow, we have to improve the graphene. So whenever uh, if we use the graphene material for the development of the device, it may be high frequency as well as the low frequency as well as the photo detector. Then we have to be use the multi-layer graphene layer so that we can improve the bandgap energy of that device. And we can use the boron nitride with the graphene. Boron nitride, but we have to be remember the boron nitride band gap is very high, so it can absorb more amount of light. But there is due to the high band gap, it also like as a insulator. So only for absorption of the light, we can use the boron nitride. Now the optical spectrum. Now the mainly the photo detector can be classified according to the wavelength, that is the UV photodetector, visible photodetector, and IR photodetector. Mainly the UV photodetector 180 to 400 nanometer frequency is cutoff frequency is 350 that we have already observed, and the visible wavelength, that is the visible photodetector, is also working in this wavelength range, and detector also working. It can have photodetector working from 1000 nanometer to 3300 nanometer wavelength. But these IR wavelength, we can classify it into the mainly two category. One is the near IR and another is the far IR photodetector. The near IR photodetector is very important, that is used for medical imaging purpose. Okay, so next part, I want to discuss the geometric structure of a pin photodetector. If we go through the photodetector, there is several kind of photodetector is available. According to the operating wavelength, we can classify the photodetector UV, visible wavelength, and IR photodetector. According to the geometric structure, the photodetector can be classified as well as classified into 3-4 categories. That is the flat photodetector, superlative structure-based photodetector, heterostructure photodetector. Mainly these three kind of photodetector are used to develop the efficiency of the photodetector. So according to the classification, the photodetector also can be classified into the two categories. Number one is the pin photodetector, another is the avalanche type of photodetector. This is, if we go through this part, then we see this type of photodetector is actually pin photodetector, and this is the superlative structure. Okay, so in the next part, if we go through that part, then I want to discuss about the avalanche photodetector. Okay, so avalanche photodetector I also want to discuss here. If we go through this structure, so this is the avalanche photodetector. This is the avalanche photodetector. This is consists of the P plus I, P, N plus. I region is the intrinsic region, and P plus where the avalanche multiplication is occurred. So in this case, the electric field is also very high. If we go through this electric field with the distance, then we see the electric field into the avalanche zone is very high. Okay, so according to the operating principle, the photodetector can be classified into two categories. Number one is the pin photodetector, another is the APD photodetector. Okay. Now, yes, if we go through the normally, this is the main region of the photodetector. This is the highly doped. In the case of the pin photodetector, if we go through the geometric structure, then we can see there is an anode and cathode is there, and as well as the cap layer is the P plus, and the bottom layer is the N minus, and the active region is the I region. And there is also the another layer is there, that is the uh, actually anti-reflecting coating. This is the anti-reflecting coating is used. Why the anti-reflecting coating is used, that part I want to discuss also here. So when the light is incident on the photodetector, then it will be mainly absorbed by the eye region. Okay, so I later on I also want to discuss the working principle of the photodetector, uh, how the photodetector actually work. That part I also want to discuss on the later. Now, if this type of photodetector is normally available, and then if we want to improve the photodetector performance, normally the performance can be improved by changing the geometry. I have already said that earlier. That is the, if we change the geometric structure, if we go through this part, then you see this geometric structure is consists of the superlative structure. How the superlative structure is formed? There is a silicon. This layer is a silicon. This layer is a 4H SiC. Then it is again silicon. Then again it is 4H SiC. So when the superlative structure is incorporated into the active region, then the conductivity of the device will be increased due to the uh, due to the quantum well structure and the quantum confinement occur. As a result, the uh, mobility of the electron will be increased and overall the conductivity will be increased. If the conductivity of it is possible, if we can increase the conductivity of the device, then the overall performance of the protector will be obviously increased. So next part I want to move. And this is a geometric structure. I have already explained that part. This is the highly doped region. If we go through the geometric structure, this is the highly doped. This is the this is also the highly doped region. This is the always the lightly doped region. If highly doped regions of doping versus the width, if we plot that, then we see the doping concentration of the P plus and N plus region is almost high, and the I region concentration is low. But if we incorporate the heterostructure of the superlative structure, then the doping concentration will be vary into the intrinsic region. That is why here the doping concentration is high, again it is low, it is again high, it is low. This is actually the happen in case of the superlative structure. So now I also want to discuss what is the basic difference between the superlattice and heterostructure. That part I also want to discuss. So if we move into the previous slide, and you see this is in case of superlative structure. In case of superlative structure, the silicon and 4HCC material are repeated continuously. But in case of the heterostructure, if we see there is only one layer will be used for silicon and another layer will be used for silicon 4H silicon. But experimentally or laboratory, we have tested that the performance of the superlative devices is far better than the heterostructure. Now, this is the geometric structure of the EPD, that part I have already discussed. Now, how another way the performance of the photodetector can be improved by incorporating the nanowire structure. How the nanowire structure that has been done? That is the P plus region and N plus region. That is the nanowire. This is a single nanowire material. And this single nanowire material, you can incorporate in between the P plus and N plus region. And then the light will be incident and the electron pair will be generated into the active region, and the current will be flow through the external circuit. Now, if we, this is a normal flat silicon material, and again you can improve the performance of the photodetector. That is, this is a multiple couple layer we have incorporated into the P plus region as well as the N plus region, and the nanowire are incorporated here in between the this and this layer, and we have tested that in case of that, in case of MGL, silicon MGL photodetector, the performance is far better than the silicon nanowire photodetector. Just 1 minute. I want to move into the next slide. And in another way, we can also incorporate the multiple number of the nanowire. Multiple number of nanowire between the P plus and N plus region. If we incorporate the multiple nanowire in between the P plus and N plus region, then we can observe that it can absorb the more amount of photon energy. As a result of the generation of the photon energy, rate of generation of the photon energy will be increased, as well as the performance of the photodetector will be increased. Now, if we go through the multiple structure, MgL silicon nanowire photodetector, I have already told that in the case of the active region, if we go through the active region or I region, then the quantum well will be created in between in the I region. If the quantum well is created into the active region, the quantum confinement will be occurred here. As a result, the overall mobility of the electron will be increased and the conductivity will be increased. If the conductivity is increased, then the overall performance of the photodetector will be obviously increased. Now I want to move into the next slide. And another way, this is very interesting things. That is the another photo detector that I also want to discuss, that we have already designed this kind of photo detector in our laboratory and tested, and this portion I have published in IEEE conduction. So if we go through this part, then we can observe that this is the intrinsic region, this is the actually intrinsic region. This is the P plus and N plus region. If this is the intrinsic region, this is the silicon material. Silicon material. We know that the silicon material, the mobility, what is the mobility of the electron, that we know. But we want to increase the conductivity, we increase the mobility of that region. So how is it possible? If we incorporate the small amount of germanium into the silicon material, then it will be the same silicon. So if the active region is consist of the stained and unstained silicon, then the quantum will be situated in between the interfaces between the unstained and stained layer, and the energy band graph also shown here, and the quantum confinement will be occurred. As a result, the overall performance of the device will be obviously increased. So, what is the importance of the stain layer in the case of the photodetector? That is, if we incorporate the stain into the active region, then the overall mobility obviously will be increased for a certain amount of the mole fraction. If we increase the mole fraction, then we see that the conductivity of the mobility of the silicon material will be increased. After a certain mole fraction, the conductivity, the mobility will be higher, and that mole fraction we have to be chosen, and these mole fraction we have to be incorporated into the intrinsic region, so that the conductivity of the I region can be increased significantly. If it is increased significantly, then the overall performance of the photodetector will be obviously increased. Now I want to move for next slide. And that I have already, now I want to discuss the overall operation of the photodetector, that when the photon will be incident, if we go through the region, that is the I region will be absorbed by the photon, and when the photon energy will be incident in this region, then the electron and hole pair will be created in the active region. And these electron and hole pair will be separated by the electric field, because we have applied a reverse bias voltage. And when the electric field will be separated to the charge carrier, then this charge carrier will be moved towards the anode and cathode, and the current will be flow through the external circuit. And that current is called the photo current. So we have to be measured the photo current, and we have to be anyhow increase the amount of the photo current. This is the energy band diagram of the photon energy band diagram. When the light will be absorbed, the electron and hole pair will be generated, and this electron will be moved towards the conduction band, and then the current will be flow through the external circuit. Now I want to come this slide next part. So first I want to discuss the what are the important parameter if we want to design the photodetector. A photodetector we can design, and then we have to be analyze the parameter from which we can say that the performance of the photodetector has been increased significantly. Mainly the parameter number one is the dark current, number two is the photocurrent, avalanche multiplication factor, photo generation rate, recombination factor, noise factor, photoresponsivity, internal quantum efficiency, and external quantum efficiency. So these all parameters we have to be analyzed in case of the photodetector if we want to determine the overall performance of the photodetector. Okay. So now I want to discuss how do you analyze the photodetector. Normally, you can use the classical deep diffusion model that is available in a published literature. That is based on the Poisson and continuity equation. But in case of the nanowire structure, we cannot use the classical diffusion model. In case of, if we use the classical diffusion model, then there is a certain limitation. That means when the quantum, in case of the quantum coil, that is, they cannot consider the hot electron effect, scattering effect, like that. So we have to be, if we want to determine the performance of the photodetector very carefully, then we have to be considered those parameters. Those parameters takes an important role also to determine the performance of the photodetector. Okay. Now, before that, I also want to describe this section. That is the another parameter is there. That is the, if we go through the structure, photodetector structure, then I want to move this structure, then you can able to understand. That is the P plus region. So what will be the width of the P plus region? What is the doping concentration of this region? What will be the doping concentration? What will be the total width of this region? What will be the doping concentration of silicon layer? What will be the doping concentration of silicon layer? So these all parameters are very important to calculate the to determine the performance of the photodetector. So these all parameters we have to be determined first, then we have to be designed, and then we have to be simulated, or you can, after simulated, we can do the go for the preparation. So whenever if we want to design the photodetector, so we have to very carefully measure all these parameters through, say, you can measure through several computer done or mathematical calculation. Then you have go through the simulation. If you get the good result for the simulation, then you can go for fabrication. So these all things we have already discussed. That the what is the type of the photodetector according to the wavelength we have discussed. The photodetector can be classified in three categories: UV photodetector, visible photodetector, IR photodetector. According to the working principle, the photodetector can be classified into two categories, that is the pin photodetector and APD photodetector. And according to the geometric structure of the photodetector can be classified into the flat structure, superlattice, and heterostructure, as well as the stem, superlattice, heterostructure photodetector. So these all things is clear. Now I want to discuss one by one these all parameter, dark current. First of all, I want to discuss about the dark current, photo current, avalanche multiplication, photo generation rate, recombination rate, noise factor. These all parameter I want to discuss one by one. First, the optical generation and recombination. When the photon will be incident in the intrinsic region, then mainly we have to, in case of the photodetector, we have to be determine the non-radiative recombination rate. The non-radiative recombination rate we have to be reduced. So accordingly, so if we want to reduce that part, so the performance of the photodetector will be increased, and then we have to be change the structure, doping concentration, everything. Now the photo generation rate. What is the photo generation rate? That part I want to discuss here. If we go through this structure, then we see the light will be incident. What that is the light will be incident here. For a particular photon energy, the amount of certain amount of electron and hole pair will be generated this year. That is called the photo generation rate. So this thing is clear. Now, I want to move into the next part. That is that the amount of photon current or number of photo-generated carrier depending on the incident optical power on the surface of the detector that I have already discussed. So in this way, we can determine the amount of the photo generation rate, and this is the formula is there. That formula P is equal to the total power. Pi is the incident optical power, and alpha equal to the absorption coefficient, and D is the length of the absorption layer. Now, another parameter that is also very important to us, this parameter. So first I want to discuss mathematically, and then I want to go for the, I want to discuss this section by graphical representation. Okay, so spectral response is also very important. That means the amount of photon, if we change the incident photon, then we see the amount of current will be changed. So that that is the spectral response reveals how the responsibility of the photodetector varies with change in the wavelength. Actually, the quantum, so the photo responsivity we can determine this formula using this formula. Another parameter is also important, that is the quantum efficiency. Actually, quantum efficiency is defined as the ratio of generated carrier flux to the incident optical flux. Okay, how much when the light will be incident, so the generated optical generated carrier flux will be generated. So these generated carrier flux to the incident photon energy. From the incident photon energy, we can calculate the quantum efficiency. So I want to discuss this part also, want to go through a problem statement. So calculate the responsibility of the photodetector with the quantum efficiency of 1% at wavelength when we consider the wavelength at 5 nanometer wavelength. Okay, so just to consider the formula of that, that is the responsibility R equal to H lambda E, and that we can consider that H nu into lambda H C. So if we put all this formula here and according to that part, so that will be, we can calculate the value of the photo responsibility. Now, I also want to discuss how do you increase the photo responsibility, performance of the photo detector. So performance of the photo detector can be enhancement possible by designing the array of photo detector. So instead of single photo detector, we can use the array of photo detector. If we use the array of photo detector, say, then it will be absorb more amount of the light energy, and the more amount of photon will be generated, and the more amount of current will be flow through the external circuit. If the current is increased, photocurrent is increased, then the quantum efficiency and the photon energy will be obviously spectral response will be increased. But in case of design of the array photodetector, we have to be remember how many number of combination will use and what will be the length of the array. That is the main factor. What will be the length of the array? That will be optimized first, and then we have to be designed. Here, if we go through this section, it's mainly designed. There is a three column is there, and row is also the three. So it is called the 3x3 array. So if we go through this section, then we see that all the photodetector are placed lambda by 4 distance. So lambda by 4 distance we have to be placed there for proper impedance matching. Now, first I want to discuss the electric field. Yes, obviously this is also important. The electric field into the intrinsic region. That if we go through this section, then we see that is the electric field. Yes, if this electric field into the I region or active region is also very important. So amount of electric field, if the amount of electric field is more, then it can separate the charge carrier very quickly, and the overall conductivity will be increases, and the rate of recombination will be also decreases. So we have already discussed the array of photodetector. So electric field. And now I want to give you one example to you that if you use the stained silicon material and unstained silicon material to develop the photo detector, then we see in case of stained material, the electric field is high, so the overall performance can be increased by incorporating the stained material into the active region of the photo detector. It is also the experimentally proved. And the dark current. Dark current is also important. What is the dark current? We have to remember the photo in absence of light. If there is no light, photon energy is incident of the photo detector, then what will happen? Then the certain amount of current will be flow through the diode, through the photo detector. That is called the dark current. So if we want to increase the performance of the photo detector, we have to decrease obviously the value of the dark current. Value of the dark current. So if the dark current is increased, if it is possible to increase the dark current, then the performance of the photo detector will be also increased. So this is the characteristics of the dark current, but the reverse bias voltage is applied along the x-axis, and the dark current amount of dark current is marking at the y-axis. Now, this is the photocurrent that I have already discussed that part, how the photocurrent is actually generated into the active region. In the case of the photocurrent, in the active region of the when the photon is incident of the detector, then it will be absorbed at the active region, and when it will be absorbed at the active region, then the electron and hole pair will be generated, and if the electron and hole pair will be generated, then the certain amount of current will be flow through the external circuit, and that is called the photocurrent. Now, I have already discussed the array and single photodetector. So, if we analyze the photocurrent in case of array of photodetector as well as in case of single photodetector, then we have observed already that in case of array of photodetector, the photocurrent is obviously increased significantly compared to the single photodetector. And photo responsibility or spectral response that I have already discussed, that is the unit as the ampere per watt. So how much amount of photon is incident and how much current will be generated. From that ratio, we can calculate the photo responsibility. So here I have already studied, we have already studied, or several researchers have already studied the array performance of the array of photodetector and single of photodetector. So in case of single of array of photodetector, we have observed that the amount of the photo responsibility is significantly enhances in case of array of photodetector compared to the single photodetector. And another part I also want to discuss that is actually also the another photodetector where we can yes, now if we go through you can use one single photodetector. That photodetector can able to detect the UV. You can make the separate photodetector for UV as well as IR as well as the visible wavelength. Sometimes we can develop also the photodetector that can work simultaneously in case of UV as well as IR as well as the UV IR visible photo detector. So this is the total length of the photo detector. If we go through the spectrum, then we spectrum already get the 200 nanometer. So it can work in the UV wavelength. We have already created a spectrum, good response in case of the visible wavelength as well as in case of IR wavelength. So we can able to detect such kind of photo detector. That also here maybe cost may be increased, but in case of that we can reduce the complexity of the system. Excess noise factor. This excess noise factor is also factor that is also we have to be reduced. So if we can able to reduce the excess noise factor, then the performance of the detector will be also enhanced significantly. This is also in case of similar things I have already discussed. This is the internal quantum efficiency analysis of the photodetector. That photodetector can able to detect the UV as well as visible as well as IR wavelength. Now the application of the photodetector, we have to be remember these things. This is very important things. I have already discussed in case of application of the photodetector, we can use the medical devices. That is the non-invasive glucose monitoring system. We can use pulse oximeter. We can use for industrial automation. If we go through that part, the optical sensor, we can use the automated system used in automated machinery systems. Then the scientific part, and this is the reference. And another things I want to also discuss here, that is the application section that we have also developed in our laboratory, research laboratory. So that part I also want to discuss here. Just wait 1 minute. Just wait 1 minute.
Okay, sir, you please take your time.
Yes. So this is also the things, another things I want to also discuss here. That is the highly sensitive oil-less non-invasive glucose monitoring system. That is also an application of the IR photodetector. That is also very important, interesting things. That highly sensitive oil-less non-invasive glucose monitoring system we can use for analyzing the blood glucose level in the human body. That section I also want to discuss this section. So what is the highly sensitive wireless non-invasive glucose monitoring system? That part I also want to discuss here. So what is this section? That is the highly sensitive wireless non-invasive glucose monitoring. We know that the invasive glucose monitoring system normally that is used for analyzing the uh, glucose level in the human body, but that is very painful and costly. And nowadays, if we go through the all over the world, the sugar patient number of sugar patient increasing day by day. So sugar monitoring is also very important to us. So if we can able to provide the very low cost non-invasive glucose monitoring system to the people, so they can easily monitor their systems. So it is also implement is also possible by incorporating the suitable amount of the IR photo detector. Uh, we have obviously observed the non-invasive glucose monitoring system is also available in the market, but that system is not too much efficiency, and that is also very costly. So here we main aim to reduce the cost of that system as well as increase the efficiency. So here we have developed the obviously this type of IR photosensor we have incorporated in this case. This section we have already discussed, that is the photo responsivity internal and external process. This section we have already discussed, so I do not want to discuss this section again. I want to move into the non-invasive glucose monitoring. This is the actually block diagram, and this is the main, that is the main part in the receiver section, that is the IR photo detector. So IR photo data, this is the prototype we have developed in our laboratory system, and then we have taken the participant data near about 400, and we have analyzed the data using the machine learning, and then we have observed there is a significant amount of efficiency is almost 92%, and we can say that the non-invasive glucose monitoring system can take an important role for the development of the highly sensitive uh, glucose monitoring system. So, thank you.
Thank you, sir. Thank you for your very interactive session based on photo detection, and your present research in this domain is also outstanding. So regarding this, I'd like to ask the participant if someone has any questions. So he can unmute himself or herself, or can put put a message in the chat box. Please. If someone has any question, please raise your hand and unmute.
I also
And
want
can
to say one thing. If anybody want to do one photo detector, it may be research work or it may be a PhD work, they can contact with me freely.
Yes. Yes. If someone has got interest in this domain, he or she can definitely contact with Dr. Abhijit Kundu for further research in this domain. So
Can I stop?
yes, sir. I
Any
think
question is
no
there?
one. I think nobody has got any questions, sir. So
Okay.
with this, I
So
would like
can
to.
I leave? Can I
No,
leave?
sir. Please, sir. Sir, wait a minute, sir.
No.
Sir, please. So, sir, please, from our side, please take this token of appreciation from Greater Kolkata College of Engineering and Management and IIT Kolkata.
Thank you.
We will send you this in email shortly.
Okay, thank you.
So, thank you, sir. Thank you for
Thank you.
joining us. So now we are closing our meeting, right?
Okay.
Okay. Thank you, sir.
Hello, Aniruddha sir.
Yes, sir. Yes, sir. Sir, tell me, sir.
Certificate of appreciation not shared.
Sir,
actually.
sir, I have shown that. Yes. Sir, is it now visible? Sir, please
No,
wait.
no.
So wait a bit. Just see. So now is it visible?
Yes, 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 yes. Thank you, thank you.
Okay. Thank you, sir. Thank you for joining us. Sir, we will email you the certificate of appreciation in the
Okay,
very
thank you.
shortly. Okay, sir. Thank you, sir. So this is basically this is due to because of the network glitch, I think.
Okay, okay, no matter.
Okay. Thank you, sir. Thank you. So,
So can I leave now?
sir, I would like to hand over to Professor Gorgopal Jana, sir. Sir, with this, can we leave this meeting?
Yes, we can end here.
Yes. Thank you, sir. Okay.